Okay, can I start?
Yes, please do.
Okay. Thank you everyone for joining to this meeting. My name is Ali, and the title of my presentation is Large-Scale Particle Image Velocimetry for Determining VENA Contractor Dimensions in Contracted Channels. This presentation shows the utility of large-scale particle image velocimetry for determining the dimensions, mainly the width of VENA contractors forming contractions of open channel flows. We use LSPIV. LSPIV is an image-based method that non-invasively measures two-dimensional instantaneous free surface velocities of water flow using inexpensive standard video equipment. This method is a convenient technique for eliminating the flow field at the surface of water body. And about the VENA contractor, the VENA contractor of a contracted flow is the narrowing of a flow as it passes through a contracted area of flow, which then spreads downstream to occupy the full width of a contracted channel. A common occurrence for VENA contractor is in bridge waterways over rivers. The concern for such location is that the contraction scour can occur in the VENA contractor region. To estimate the depth of a scour to design bridge foundations, it is necessary to determine the width of VENA contractor associated with the contraction scour formation. Here is an overview of the flume setup that we used for this investigation. This flume was 80 feet long, 8 feet wide, and 4 feet deep. Here, three different contraction ratios were investigated in this study, which involved 19 experiments, including different discharges and bed conditions, such as fixed bed and erodible bed. Here, you can see three different contraction ratios that were used for this study. Here, the B1 is the width of approach channel, and B2 is the width of contracted channel. In this picture is the narrowest one, this is the intermediate, and this one is the widest. All the pictures are for the erodible bed conditions. In this study, a software card for the LSPIV was used for measuring the VENA contractor width. The LSPIV technique calculated the movement of paper tracers on the water surface flow to and within the contraction intervals. Most of the applications were done once the contraction scour had attained an equilibrium condition. The flow should be seeded by paper pieces, and a video should be taken. Then the video is uploaded in software, and the procedure includes orthorectifying the images. Here is an example of an orthorectified image. And the next step is calculating the instantaneous velocity vectors. Here is an example of instantaneous velocity vectors. As you can see, it includes ground velocities with some directions and wrong magnitudes. So we need to apply a filter on the magnitude and the direction of velocity vectors. So here is the instantaneous velocity vectors after applying the filter. The next step is calculating the average velocity vectors for all the time steps, and then calculating the velocity contour map and streamlines. In this picture, you can see the average velocity vectors for all the time steps. And here is the velocity contour map. And finally, this picture presents the calculated streamlines. All the results from different values of contraction ratio, B1/B2, and discharge were uploaded into an AutoCAD file. Then the images were scaled and the VENA contractor with B2 prime was measured. Here you can see the VENA contractor with, which is the narrowing part of the flow. This is the VENA contractor with, which is orange. This table presents the measurements for all the experiments. In this table, we indicate the velocity at upstream, and FR is the Froude number of the uniform approach flow at upstream. And also there are some data about the discharges, the contraction ratios, and velocity. The data from the table were plotted here. The vertical axis is KV, which is the VENA contractor coefficient, and the horizontal axis is the dimensionless number that shows the properties of the flow, including the velocity and the contraction ratio. This plot has two curves. This one is the VENA contractor for the rodable bed conditions, and this curve is for the fixed bed conditions. Using this plot is very straightforward. We need to calculate the Froude number at the upstream and multiplying that number to contraction ratio -1. And after that, we can read the KV value, which is we can then find the VENA contractor width from the vertical axis. The LSPIV technique was useful for estimating values of B2 prime for most of the experiments, and for the smallest value of B1/B2 the use of LSPIV required the use of judgment because turbulence made the boundaries of VENA contractor unsteady. The use of LSPIV in conditions where the water surface was wavy, causing vertical motions of water, did not result in reliable estimates. The estimates of B2 prime were considered sufficiently useful to delineate the VENA contractor extent for purpose of hydraulic engineering design. I'm happy to hear your questions. Sarah?
Yes, we have a couple. I'm actually going to turn on Mashid's microphone and see if we can have her ask you directly. Let me see if this will.
Hi, Ali. It was a great presentation.
Thank you.
So I have one question. In the table that you showed, you told that you calculate the Froude number at the upstream. Why you didn't consider the velocity at the downstream?
Okay, let me show you this. The reason that we use the Froude number at upstream is that the geometry of the bed at the upstream does not change during the experiment, so it's constant, and we can rely on our data here. But here at the contracted region, we have erosion, and the bed doesn't have a uniform geometry, so almost it is impossible to calculate a Froude number at that region. So the reason that we use the Froude number at upstream is that. Okay. Did I answer your question?
Yeah, that makes sense. Thank you.
Yeah.
Great, thanks. So again, you can enter questions into the chat queue or raise your hand and I'll turn your microphone on. I'll just give it another minute or two here.
I have a question.
Yeah, go ahead.
Ali, did you consider using more pieces of paper when you were doing the LSPIV?
You mean the number of papers that we use for seeding the flume?
Yes, yeah, exactly. The small particles of paper that you use to measure the surface velocity.
Yeah, we use lots of papers. I don't have I cannot give you any number for that. I can see a bag full of piece of papers because for the LSPIB we need a good coverage of paper pieces on the water surface. So
right.
We seeded the flume as much as possible to get a good sequence of video with a good coverage of paper pieces on the water surface.
Gotcha.
Yeah, exactly.
Okay. Are you aware of, do you know if other people have tried using more or less pieces of paper to get, better resolution surface velocity measurements?
Actually, there is not a certain number for paper pieces because it depends on your velocity. When the velocity is very high, you need to seed the flume very fast with a large number of
papers.
papers.
Right.
When the velocity is low, so you don't want to make a bunch of paper on this water safe surface. They are stuck to each other and it causes I cannot give you a certain number for paper based on the velocity.
Yeah.
It depends on the judgment, I think. Yeah, did I answer your question?
Yeah, you did. Thank you.
Yeah, you're welcome.
Great. And Jessica, I saw your mic turned on. I muted you. I wasn't sure if you had a question or if you just bumped the microphone button. Okay, well, I haven't seen any other questions come on, but we're going to stick with our schedule. So we will resume at 10:40 for our next presentation. So if anyone needs to get up, stretch your legs, grab another cup of coffee, feel free to do so, and we will start back up at 10:40.